Okay, so in this problem, we're going to again try to write the equations for slope and displacement. Following some of the other ones that we've looked at, since the load is continuous, it'll be easy to write a continuous expression for the moment across the structure and then integrate it with direct integration and find the displacement and the slope. So again, I'm going to talk about making a cut, say at some distance x, and ask you whether it's best to go left or right. And again, right is not difficult, it's more tedious, I think. I think the left-hand side will be a little easier to deal with. So we'll go with the left side, and since I've made that choice, I would need to know my reaction at A. So I'll assume it acts up. With that, I'm going to do the equilibrium of the whole structure to find that reaction. So I'm going to some moments about point B. Make sure it's in equilibrium to solve for AY. And also, again, I'm going to use right-hand rule for my sign convention. Now what I need to help me with this is the concentrated equivalent force of this distributed load. Now we know since it's a triangle, it's going to occur over here on the higher side, the higher intensity. And of course the area of a triangle is 1/2 base times height. So this is going to have a value of WL over 2. And the distance from B will be L over 3. So with that information, I should be able to solve and find AY. So summing moments about B, my concentrated equivalent force creates what kind of moment about B? Positive or negative with this sign convention? Positive. So I have a force of WL over 2 and a moment arm of L over 3. And then AY creates negative moment, and it has a moment arm of L. So it looks like AY is going to be WL over 6. Okay? So let's come down here and draw the free body diagram of this section to the left. I'll have my reaction I just found, WL over 6. I'm going to have to deal with this triangular load, which we'll talk about in a second. The length of the element is x, and I will assume positive moment at the cut. Now what is the intensity of the load right here at this high side? Well, first let's go back and what's the slope of this line? Slope is rise over run, right? So that's W over L. The intercept is 0, so it looks like that value right there is going to be Wx over L. Does that work? Well, when x is 0, this should be 0, and that matches really well. When x is L, L over L is 1, and I get W. So that's really the equation of this line in our coordinate system. Now once you know that, the rest rolls around pretty quickly. So again, I'm going to have a force. My force is going to be the area of this triangle, which is 1/2 base times height. So I'll write it out this way. So there's 1/2 base times height. Just want you to see all the pieces. We'll clean that up in a minute. And of course we know the distance here is x over 3. So now I'm going to sum moments again at this cut that I just made. And again, make sure I'm in equilibrium. So what do I get? Well, my internal moment with my sign convention is positive. The moment of this concentrated equivalent force about the cut is also positive. So let's tidy this up. It looks like I've got W x squared over 2L. So W x squared over 2L. That's my force, and then this is the distance, x over 3. And then I have my resultant force, which creates negative moment, and that's WL over 6 times x. So now I can solve for the moment. So the moment as a function of x is going to be, there is a W there. What else can I pull out? Not really anything right away. I think I'll just pull out the W for right now. So the first one will be x cubed over 6L. Did I do that right? Looks right. And then this will just be XL over 6. Well, that's convenient. So I could pull that 6 out. I could do something with these L's to tidy that up a little bit if I wanted to. In fact, I think I will. Might make it a little easier later on. So I'm going to pull this L out here, and that's 6. So I'm going to end up with WL over 6 is my constant. And what that gives me in the first one, that L cancels, so I just get minus x cubed. And then when I pull that out, I did that wrong, didn't I? Yeah, I did that wrong. I should have divided by L. I messed up. You know what? Let's just leave it like that right now. I'll just scratch that out. There's no erase, unfortunately, here. That's good enough. Does it work? Well, the moment at x equals 0 should be 0. And check my equation. I put in x equals 0, x equals 0. That's right. What is the moment at x equal L? At the pin at B. Should also be 0. Put in x equal L, what do you get? You get L squared, negative L squared over 6 plus L squared over 6, again, is 0. So that seems to work. So I feel pretty good about my moment equation. So now it's time to integrate. So we know that the slope is the integral of the moment divided by EI. So we just need to integrate that thing. Maybe I'll take another shot at tidying this up. So I've got a W and a 6, and I pull out the L on the bottom. Yeah, so that'd be W over 6L. Oh, forgot my integral. This is an integral sign. So I'm left with what? Minus x cubed, and this will be plus XL squared. Did I do that right?
6L EI.
Oh yeah, where did my EI go? I'm going to squeeze it in. I6EL. Thank you. That looks like a mess. I'll tidy it up next line. So here we go. So what's that going to be? That's going to be W over 6LEI. And the first integral will be x to the 4th over 4. And the second one will be x squared L squared over 2. And integration constant. Do I know anything about the slope in this structure? I know somewhere in here it's going to be 0, but I don't know where right now. So I got to leave it alone. So let's integrate it again. Why not? You guys are good integrators. So let's integrate the slope to get the displacement. So I'm going to integrate that thing. So again, I'm going to have my W over 6L EI, and I'm going to integrate this thing, x to the 4th over 4 plus x squared L squared over 2, plus I'm going to integrate C1, and what do I get? Well, my term in the front stays the same, and I get minus x to the 5th over 20 plus x cubed L squared over 6. What's the integral of C1? C1 x, and then I get another integration constant, C2. Now, just like we did in the previous problem, we're going to evaluate these two constants by matching the equation through the 2 points that we know. So we'll start with A. In that case, we know that the displacement at x equals 0 is 0. So plug in x equals 0. 0, 0, 0. All I have is C2. So C2 looks like it's 0. That's nice. It's out of the problem. And then at x equal L, the displacement is 0. That's our point B. So I got to put an L in all this stuff. So I've got W over 6L EI. That's my constant. This is going to be minus L to the 5th over 20 plus L to the 5th over 6 plus C1L. I just have to solve for C1. Looking for some way to make these work, the only thing I can see is if they have a denominator of 60. So this would be 3 60ths plus 10 60ths gives me 7 60ths. Then the 60th times 60 is 360. Right? And then this L knocks that out to L to the 4th. And you divide by that L, you get L to the L cubed. Right? So C1 should be minus WL cubed over 360 EI. Is that right? Oh, I forgot the 7. 7 WL cubed over 360 EI. See, nothing to it. So what's my expression for displacement? I got to put C1 back into there. That's going to be a massive headache. I'm going to try to find this W over 360 EI somewhere. So I'm going to do that. So I'm looking at the first term. There's a 6, and that's 120. That's 3 short, right? So this is going to be minus 3x to the 5th. This one's going to be 10 short plus 10x cubed L squared, and then minus 7L cubed. Did I do that right? No? Bueller. Is that too old a reference? It used to be a good reference, then it fell out. But then the movie started running on TV a lot, and then it came back. Has it gone away again? It's back? Cool. So does this work? No? It doesn't work? Well, it should work when x is equal to 0. Oh, I left off an x. How's that? No, something's still not right. I lost something along the way. Oh, I forgot this L here. Oh, shoot. So that means that if I pull an L, this has to go to the fourth. Is that right? And then I have to get an L out here. Oh, this is turning into a disaster. I think that's right. Because now all the terms are linked to the fifth. X to the fifth, 5, 5. It does work because you put an x equal to 0, it works. And you put an x equal to L, you get -3 plus 10 minus 7, it works. I may have gotten a little messy at the end. I think that's right.
That other L term have to be...
It was here and I forgot it.
Right, in your y-x equation.
So I added it, right? This would have had cubes, so when I pulled an L out, I made it to the fourth.
So that other L term, then 10x cubed L to the second, which is next to the L cubed.
This one?
In your bottom equation? Yeah, that L right there.
Well, that L's already out.
Okay.
Sorry about that. You can see they get a little tedious. So any questions?
TFL.